To summarize, the AutoQoS Voice over IP macro automatically optimizes your frame relay connection to support voice over IP traffic. All we have to do is configure a point-to-point subinterface, properly set the bandwidth, and enter the macro in ccnp-ccie configuration mode. When we use the trust keyword, it is assumed that all traffic marked dscp-ef is voice traffic. It is put in a priority queue, compressed, and goes out the interface first. Voice signaling traffic is assumed to be marked CS3 or AF31. If the queue becomes congested, up to 5% of the bandwidth will be reserved for it. Data traffic has the lowest priority. It will be fragmented if necessary so as not to slow down the voice packet. In this presentation, we will examine 5 methods of prioritizing traffic over frame relay: simple priority, low latency queuing, ccnp-ccie priority, PIPQ, and the frame relay broadcast queue. These methods differ in terms of how they identify traffic and where they can be applied. The traditional method of priority queuing in Cisco IOS involves associating traffic with one of 4 queues using a priority list. This list is then applied using the priority group command. This method has the advantage of providing up to 4 different levels of priority. Its disadvantage is that higher queues can starve lower queues. We have a lab set up with a traffic generator. It sends 40 kilobits of traffic per second to each loopback address on R2, for a total of 80 kilobits per second. However, the clock rate between R1 and FRS is only 64K. We have applied a policy that simply counts the traffic inbound R1 and inbound R2, so we can see the effects of various priority configurations. Here's the traffic as it comes into R1. We enter Show Policy Map Interface to see the traffic counts for each class. Class map 112 matches on traffic destined to 10.1.112.100 on R2, and class map 113 matches traffic destined to 10.1.113.100 on R2. Notice we are getting a steady 40K of each type of traffic inbound R1. Now let's see how much of this traffic actually arrives on R2. Because the clock rate between R1 and FRS is only 64K, only about 32K of each type of traffic is actually getting to R2, about equal amounts of each. To demonstrate priority queuing, we will prioritize traffic as it leaves R1 on the frame relay network. Highest priority will be given to traffic destined to address 10.1.112.100, and lower priority to traffic destined to 10.1.113.100. Here is the priority list that we'll use first. It assigns traffic destined to the 112 address to the high queue, and traffic destined to the 113 subnet to the medium queue. We will apply this list to the S00 interface queue on R1 using the priority group command. First we go into the major interface S00, enter the priority group command, then we're going to clear our counters and turn on a debug priority. Now let's go over to R2 and see what effect this has on the traffic. We'll just repeat our Show Policy Map Interface command. And the traffic counts are starting to come up. We see 36K for class 112, 27K for class 113. Let's re-enter this and get some fresh statistics. Now the counts are up to 40K for our priority class, class 112. Class 113 is only at 23K. Adding these together gets us our 64K clock rate. We'll enter this one more time just to make sure that these numbers are consistent. And here we are about 40K for 112 and about 24K for class 113. Most of the traffic, just about all of the traffic in our priority queue is getting to R2. The traffic in the medium priority queue, class 113, is getting cut about in half. Let's go back to R1 and examine the details of the priority queuing. First, we'll take a look at the interface counters by doing a show interface S00. And we'll move down a little bit further in the output. Notice that the queuing strategy says priority list 1. Below, you see the details for each of the 4 queues: high, medium, normal, and low. Notice that no packets have been dropped from the high queue. The medium queue is full, all 40 packets, and to this point, 296 packets have been dropped from the medium queue. Earlier, we entered the command debug priority and sent the results to the log. Let's take a look at that log now. Every packet that matches our priority list is referenced here. Note the traffic to 10.1.11.12 is put in the high queue, and traffic to 10.1.113.100 is put in the medium queue. The debug tells us each time a packet is dropped because of a full queue. Let's take a look at those packets that were dropped due to congestion. We'll simply filter for the word congestion in the log. Note that none of our high priority packets were dropped. Only traffic to 10.1.113.100 in the medium queue shows as congestion dropped. By default, traffic is placed in the normal queue. Let's do a ping to test this. First, we'll clear the log entries, then we'll do an extended ping to generate some traffic, and then we'll examine the log. Ping is failing. Let's see if we can figure out what happened to them. We'll filter the log for the term normal. Notice that all of this traffic defaulting to the normal queue is getting dropped. Let's take a look at our show interface to see what the normal queue looks like now. Here you see the normal queue. It has a size of 60. It's completely full, and a total of almost 2,000 of these packets have been dropped. Still, however, none of the traffic in our high priority queue has been dropped. All 40K of the traffic destined to subnet 112 is being prioritized and sent across the frame relay network. When applied at the interface level, priority queuing affects traffic on all subinterfaces and all PVCs. To apply priority queuing at the PVC level, you must first create a queue for the PVC using a shaping tool. Simple priority queuing uses traditional frame relay traffic shaping to create per PVC queues. The priority group command is applied to the PVC inside a map class frame relay. To try this, we first create our map class frame relay. We'll call it map class. We're setting our CIR to 64K and also the min CIR to 64K. It's important to set min CIR in our case because min CIR is the maximum reservable bandwidth, and it defaults to just half the CIR. Next, we'll go into interface S00, remove the previous priority group command, enable frame relay traffic shaping, and apply our map class to PVC 112 on subinterface S00.2. We'll clear our counters and also clear the log. Now let's go over to R2 and check that the traffic to subnet 112 still has priority over the other traffic. We'll simply take another look at our policy map. And still, class 112 has about 40K of traffic arriving, and class 113 has only about 24K. Let's go back to R1 now and check out just how this frame relay queuing is operating. First, we'll just do a show interface. Note that at the interface level, the queuing strategy just says first in, first out. The show command that we're looking for would be show frame PVC 112. Down towards the bottom of this output, you see that the queuing strategy for this PVC 112, references our priority list. You see the list laid out for you here with access list 112 associated with the high queue and access list 113 associated with the medium queue. You also see that our 4 queues have been moved to the PVC level. Again, the priority queue is empty and hasn't dropped any packets. The medium queue is full and has dropped over 400 packets. Let's examine the debug output in the log. Notice that the output now specifies the particular PVC, not just the physical interface. Cisco's preferred method of priority queuing is low latency queuing. The priority command is used in a policy map to specify the class of traffic to receive priority treatment. You also specified the maximum bandwidth for the priority class. This keeps the priority class from starving out lower priority traffic during times of congestion. When the link is not congested, however, the class can take as much bandwidth as is needed. To demonstrate LLQ, we create the class map and policy map. We then replace the priority group command in the map class with a service policy command. Here's our policy map. By default, the priority burst parameter is 20% of the configured rate. We set to 1500 bytes to match the MTU. We can verify low latency queuing using the show policy map interface command on R1. You see here that the statistics associated with LC112 on serial 00.2. Notice the offered rate of 40K and a drop rate of 0 for the priority class 112. The traffic destined to subnet 113 falls into class default and is being dropped at a rate of about 16K. We can also verify the low latency queuing operation by looking at the results on R2. Note that R2 is getting all of the traffic destined for subnet 112, but only about 23 to 24K of the traffic destined to subnet 113. This is cut back from its original 40K. In this demonstration, we used FRTS to create the PVC shaping queues. In the Voice over IP presentation, we show you how to create a PVC shaping queue using the MQC instead.